Okay, so let's start. And here we will try to talk a little bit more about the formulas and equip you with some formalisms and so that you could solve the homeworks, and it's more sort of seminar-like or tutorial-like. But we'll continue with the lecture, and then we'll get more technical on the details. So in order to introduce the, I guess, Schrödinger equation and or explain how it is related to more classical physics, here the example is something that you should probably familiar with from the general physics, right? So Newtonian equation, and what do we have in the classical mechanics, and then we'll see how that is paralleled in the quantum mechanics, right? So what I started before is with this Newtonian formula, F equals ma, right? And if we look at it's an ordinary differential equation of the second order. So in the classical mechanics, in order to describe behavior of the particles, and this is going to be very simple, right? So if we, let's say, look at the particle that is suspended in the air at time 0, right? So, and there is a gravity acting down, right? So, and there is a potential energy that wants particle to go down. So then we could obtain, using the Newtonian equation, the trajectory of the particle x as a function of t at later time by solving differential equation. And this is something that is going to be parallel to solving something similar, but now in quantum mechanics with Schrödinger equation. All right, so with Newton equation, the procedure is that we formulate the second derivative, which is a, right? We multiply by m, and then we have a force, right? So the force is negative derivative of potential. Now, the potential energy is just mg times the height, right? And so the way we present the problem, the x is not only the coordinate of the particle, but it's also the level from the kind of the top, like how high we are, right? So the x coordinate is right here. And then the potential will be mg times the height, x. And so the force will be the derivative of the potential energy with respect to the position, x. So that gives us, when we differentiate mgx, that gives us minus mg, the minus here, right? And m can be then essentially removed by cancellation, because m is on the left-hand side from ma, and on the right-hand side from the potential energy. Now we have a acceleration which is minus g. It's against the gravity, right? So, or it goes like the trajectory of particle goes along the gravity, trying to reduce the height, because we start with x and the x goes up, right? So, but we know that if we release the particle, it goes down, right? So that's why acceleration is minus g. G is positive, 9.8 meters per second square. So we start solving this differential equation by integrating out the time. We first integrate once, and we get the velocity at time t equals to velocity at 0 time minus gt, because we just, if we integrate here, we get the extra time. So this integration step, is it clear, or do I need to go more into the details? Everybody are familiar with the integration at this level? If there are no questions, then we just do the integration one more time to get rid of the derivative of x with respect to t, right? So to get to the trajectory x of t, right? And when we do this integration, this quantity here is velocity at time equals 0, the initial velocity. So that is constant, that initial condition that is supposed to be given for us to solve this problem. And when we integrate the second time, we get t in front of this initial velocity, v of t at 0. And we get the integral of the t to the t squared divided by 2, right? So that's the integral from this term. And we have our trajectory written now as a function of time. It's almost like probably high school material, really. This formula sometimes is given in high school. How do we construct a trajectory as a function of time, right? For things like this. And this is a simple case where the solution that we're looking for is position as a function of time. Or we could, for the full description that's enough. In principle, you could also look at the momentum as a function of time. So the pair position and momentum fully describe how the classical particle behave. And so then another example here, which we skip for now, is first order kinetics. It's something that we also can do. Their differential equation is also very simple to solve. But essentially, what I want to get to is that the Erwin Schrödinger is kind of formulated just a different equation for describing quantum objects. Now, this equation is very similar to Newton's equation, but the quantities that we have in the Schrödinger's equation, they are more complicated. But it's still first order in time differential equation, and there will be second order in the space. Okay. Now I will slowly introduce all the parts. We will talk how to write Schrödinger equation for molecules, and then how to solve it, what to do with the solution, things like that. So let's start, and hopefully you could follow it. You could ask questions, of course, along the way. So this is the equation that is the fundamental equation that we will be solving, and it has this operator h essentially on the left hand side. The operator is nothing but just the two terms, t plus v. T is the kinetic energy operator. T plus v, that's the h. And the kinetic energy, as we discussed before, it just comes from p squared divided by 2m from the momentum. That's why it has this second derivative. And then there is a potential part that is just the potential energy of the particle. As in the classical particle, we had the gravity. In the molecular systems, we will mostly have Coulomb interaction and other terms that kind of come in from the Coulomb interaction. But you could think of, if you want to think about molecules or particles inside the molecule, like electrons and nuclei, they mostly just attractively interact through Coulomb, and we will talk about this more in details. Now, the object that we need to solve for is this wave function that is a complex object, literally complex, meaning that it could be a function that has a real and complex part. There is not much complex analysis we will need in this course. It's mostly that you are familiar with the complex numbers and how to operate mostly with the I, and we'll talk about that also in a moment. But as like before, in the classical case, we had x as a function of t, and that was a very simple object. It's just a function of time, where position of my particle as a function of time. Now, in the case of quantum particle, we have this wave function as a solution of Schrödinger equation, and that object is, well, in the simple one-dimensional case, which we will start with, it's the position, right? And the wave function, even if we put aside the fact that it could have a complex part, it's still a function, right? So at the zero time, it could be a function, and then at later time, it's a different function. So it's changing with time. Okay. And on top of that, the more particles we have, like let's say water molecule, we have for every particle that we have in the system, we need a coordinate. So the function that is a solution of Schrödinger equation becomes more and more complex object because of this coordinate dependence. Okay, of course, most of the stuff, in order to understand, you don't need to go into the multidimensional cases, because in multidimensional cases, we would need to, it's really hard to draw the things that are solution essentially of the equation. Now, I would like here to illustrate you this concept of the wave function and solution of the Schrödinger equation by example, where it's a simulation that done on a computer, and it shows how the classical particle behave versus quantum particle behavior. Okay, so there's a script that I will run. Okay, so this is a script. What it shows, let me explain what it shows first. So we have here the kind of the potential energy in black right here. Potential energy, and you could see that the space coordinate x, it's a one-dimensional problem. There is an x coordinate, right? And potential energy first is 0. It's a flat surface. And then there is a sort of inclined surface, inclined plane, right? So now what this red and blue is a wave function at the 0 time, right? So the blue one is the real part of the wave function, and the red is complex part. So we have a function that that has two components, real and imaginary, right? And so that's our wave function for a free particle. As you could see, roughly it's localized in some part of the space, and that's where we can find our particle. Okay, so that the probability of finding the particle is pretty much where it's localized. And now if we solve numerically the Schrödinger equation on a computer, that's what this script is doing. It will describe how, if we give initial velocity to the particle, how does it move, how the wave function evolves as a function of both space and time, two components. And in order to see also how the classical particle behaves, I have here the black dot is going along the way. I think it's black, yeah. So it's a black dot going along the way. As you could see, roughly where the quantum wave function is localized, that's where the classical particle is, right? So the equations that these two objects kind of governed by, they're different. For a quantum wave function, it's governed by the Schrödinger equation. The classical particle, this black dot, it's governed by Newtonian equations. As you could see, roughly, they're going in a very similar trajectory, right? So what you would expect is if you have a ball on the surface with inclined potential, like this essentially inclined surface could be seen as a potential, right? So you flick the ball, you give the initial velocity, and it will go up this inclined surface and then loses all the velocity, all the momentum, and goes back, right? So, and it goes back and stops, not because it will stop here, it's just because the simulation stopped. In reality, it would just keep continuing going left, right? So because of the like force that inclined surface exerted on the particle. Now, as I was saying before, this wave function object is not observable, and what kind of observable, one of the most important observable quantity that we will talk about, it's the probability density. So that we could also illustrate by just taking absolute square of the wave function, and this is this pink, like Gaussian shaped looking probability density. So that object is essentially describing, if you integrate the area under it, it describes how probable is to find the particle there, right? This is a different representation. I still, in order to solve the Schrödinger equation, use the wave function, but what I represent as a solution here is a green dot as a classical particle. As a solution, I just represent the probability density of the quantum particle to see how it changes. So here we could see, without all this unnecessary wiggles, you could see that when the quantum particle bounces off the wall, there were some ripples, right? So that means that the probability of finding particle off the center of this Gaussian is increasing, right? So that's kind of interesting feature. And we will see more simulations, but this is the first one that shows that essentially the point of this simulation is that quantum solution of Schrödinger equation is very much similar for some potentials to how classical particles behave, right? That's why in many cases, quantum mechanics reduces to classical, but there are, of course, cases where that's not the case. And just to give you examples so that it doesn't look like we always have quantum and classical being the same. So this is a tunneling process. So okay, so what's happening here is that there is a potential in black, right? And what the starting point was that a wave function is localized in one well, and we then let me restart, and we let the wave we let the let me just make sure that we share the plot. Right. Okay, and we let the system to evolve. So as you could see, the probability of being in a different well is increasing with time. and where the system was initially is reducing, right? So this could be seen as a illustration of, let's say, a chemical reaction where one, like hydrogen, is moving between the wells in some molecule, right? While classical particle, because we were not given any like velocity towards the other well, it just stays there and it doesn't really move anywhere. So quantum and classical behavior in this case is very different. Okay, so this is an example where things are very different. Now, let's skip this and let's talk about right. Let's do a little review on the complex numbers since they will be appearing in our wave function treatment, and make sure that everybody can comfortable with the complex numbers. Now, I already mentioned the part like this I is a square root of -1, right? So, or square root of I is -1. So that's already probably very well known by you guys, right? And we then can do the arithmetics like taking the square root of negative numbers. This will be just a review of how do we operate doing the basic operations with the complex numbers like any complex number will have real and imaginary part, x and y. Here, the notation will be like real z and imaginary z will be giving us x and y, right? And then what we can do with the complex numbers, we could add them up. Addition of complex numbers is very straightforward. We just go and add the real and the imaginary parts, right? So there's no mystery here. And then we could, since it's a sort of mathematically speaking is a field, so we could multiply as well, and we could also divide, right? So multiplication goals, it's a little bit more complicated because now we could multiply real with real, imaginary with imaginary, and real with imaginary, right? So there are a few more possibilities. It's not just real, real or imaginary, imaginary. And so the thing to remember here is that when you multiply I by I, then there's I square, which gets you back to real, right? So because I square is -1. Okay, so the multiplication of complex numbers should be relatively straightforward. Now, the operation that you should not forget about, and we will be using it quite in a few places, it's a complex conjugation. So complex conjugation is essential, and what it does, and it's very simple, right? So we take the if you take the z equals x plus iy, then the z star, that's a conjugation, that gives you just a change of the sign in the imaginary part, right? So if it was I with plus, then it switches to I with minus. If it was with minus, then it switches to plus, right? Here are some examples, right? If we do the conjugation, the only part that changes is the imaginary part, right? So the real part stays the same. So for the real numbers, the z and z star are the same. So if we find in some problem that z equals to z star, that means the z is a real number. Okay. Yeah, so the real number conjugation is number itself. And why is this conjugation is important? Because one way to get the real numbers for sure from the complex numbers is multiplying any complex number with its conjugate, z times z star. And that operation is also called absolute square. So there is another symbol for this, is a z squared with an absolute sign, because, and this is z star, or z star z, they do commute in multiplication. So these are the same. Okay, so the reason to do this absolute square instead of just a square, because the square of the complex number is not necessarily a real number, right? But absolute square is always real, and it's always more or equal than to 0, right? If the number is if z is 0, then you get 0, but in other cases it's always positive. And that's the explanation why it's this nice algebra that shows you that really you get all the complex parts then gets cancelled, and the I times minus I will give you positive y. So that is the anatomy of getting the absolute positive number. And also keep in mind that z times z star, or absolute z square, is not the z squared in principle. So don't confuse those two operations. For the complex numbers, they are different. Okay, here's the example. How do we do the complex number absolute squares for this 3 minus 5i? That's how we do it, and we get 34 in this case. Okay, so now the part that is a little bit more complicated is division of complex numbers. So in order to divide, which we won't do much, I think, in this course, but just in case, to remind you how do we divide, let's say 2 plus 3i, divide by 4 minus 5i. This is how we do it. We multiply the denominator by complex conjugate. And so what this allows us to do essentially is to get a completely real positive denominator, 41 in this case. And then to keep things the same, we multiply the numerator by the same, right? So, and that gets us all the complexity only in numerator. And so then you just do multiplication in the numerator, you get the complex number, but the denominator is real and positive, so you get the answer written as a real plus imaginary part. Okay, any questions here? Now there is I guess another way to represent, there are multiple ways to represent complex numbers. One is just real and imaginary components, and there is also like thinking about them as in polar coordinate system, where there will be they're essentially like vectors in the 2D subspace, right? So the real part is the x and the imaginary is y, and then the number itself is a point in this 2D plane. Okay, so that's one reason why we cannot say which complex number is bigger and which one is smaller. So there is no order of complex numbers, simply because they are like points in 2D space. How do you compare points in 2D space? There is no comparison, right? So, but then there is another representation that is related to the polar coordinate system, and it's could be motivated first by thinking about earlier formula. And the earlier formula, I don't know, like, do you guys are you familiar with do you know it? This expression that is very useful. It's exponent of I theta gives you cosine and sine. And it's very useful because you could then express cosine and sine in terms of the exponents, right? And many trigonometric kind of relations, like product of two cosines or sum of two cosines, could be just reformulated in terms of the exponential functions, which are easier to manipulate with. Okay, so this earlier relation is going to be useful for us. Now, one operation that we'll be doing frequently is conjugation, right? And so since the earlier expression has a I theta in the exponent, right? So then the conjugation of that is minus I theta. And so the exponent also is convenient for the multiplication purpose. Now, where this is useful is to present the complex numbers in terms of, instead of x plus I y, we present them as r times exponent of I theta, where x and y are functions of r and theta, right? So that, do I have a picture here? No. Yeah, so the picture would be something like this. If we have x and y, then this vector, the length of that vector is r, and r is square root of x squared plus y squared, right? So that's the point. And then the theta is the angle here, so that the x coordinate is exactly r times cosine theta, and y coordinate is r times sine of theta. Okay, so this is a polar representation, and you could switch back and forth between the two if needed. Okay, so now complex valued functions. We will often encounter functions whose values are complex numbers. Here's one example. Function is like this, and it can be written then as x times cosine of x minus x times sine with I of x, right? And so the general format is that this complex function is u of x plus I omega x, right? So this is a real part and imaginary part for the function. And then we will need to differentiate and integrate sometimes these functions, but all these operations, integration, differentiation, calculus operations, they will be done for the real variables. All right, so we will not differentiate with respect to complex variables or integrate with the complex variables. So that's why I is just a special constant that essentially separates the real and imaginary part. And also, if I squared, then you get the -1. So that's the only thing to remember. Now, here's the example that if we differentiate this function, I is again just a constant, and we differentiate sine to x in the normal way. 2 comes out, and sine gets to the cosine, right? So differentiation and integration will be like a real calculus differentiation and integration. There is a nice area of calculus that talks about how to extend the differentiation and integration into the complex variables. Let's say d over dz, where z is a complex number. That calculus we won't use, and it won't be necessary. All right. So, but it's a very useful thing, but not so much in our course. Right. So this is now the example where the I again is just like a constant and is treated like a constant. When we differentiate, you just get ik in front and so on with the differentiation, let's say here for another function. Any questions so far on this reminder? How do we deal with complex numbers? No questions, then okay, so we will need to do the complex conjugation of functions. And again, the procedure is relatively simple. We just change the sign in front of the component that is multiplied by I, right? So here are two examples. If you do the conjugation, we just change the sign here and here. Now, the product like this we will encounter quite often because we'll have a probability density for particles described by absolute square of the function. And this is going to be written like this, f times f star, or f absolute square. It's a real value function for the same reasons that absolute square of any quantity is going to be always real, positive, right? And here are some examples. Again, if this function is taking absolute square, we get a function multiplied by its conjugate, and we get just x squared. Note that very frequently we will get rid of the exponential function of I x or I something by conjugation. It's just going to become identity. Not zero, but identity. And here's another example of taking a function and doing the complex conjugation. Here we have this result because of the conjugation again. Okay. All right. Any questions? How to conjugate, how to do stuff? If not, let's see. Now, I guess the main equation will be this time-dependent Schrödinger equation for us, this one here. And we will roughly could separate three main goals here for our course. How do we construct it? How do we solve? And how do we use the solution? So that's those are the three things. And we already start talking about the construction somewhat, but we will, of course, dwell more onto that. So for construction, we would like to know, okay, if we have a molecule, how do we construct? What is the H? How many variables the function has? What is I and H bar? We already seen. This is just a reduced Planck constant. I is imaginary unit. So why are they there? That's again, the answer is that just this equation cannot be derived. It's just an equation that makes sure that the results agree with the experiment. Now, solving it is relatively complicated. We will look at the simple systems later in the kind of the middle of the semester. And first, we will study the quantum formalism from the point of view of, let's say, somebody solved, like on a computer, or analytically, somebody solved this equation. So what do we do with the solution? How does knowing the wave function allow us to say something about the system, right? Because in order to go and solve, like, motivation for solving it is to know what you will do with the solution, because the solving is usually takes quite an effort to do. All right, and here let's talk about the physical interpretation of the wave function. If somebody solved this problem for us, so what do we gain by knowing what the wave function is? And here we will discuss the probability density. I guess we start today and we will continue next time, right? So, but this is kind of a very important aspect. So one of the cornerstones of quantum mechanics is that this wave function by itself, as I said, it's not observable, but it gives you access to all the properties that you potentially wanna know about the system, all the properties. And one of the most important property is really where it started. It's like, where is my particle, right? So if you solve Schrödinger equation for a particular particle, which is the simplest case compared to, say, multiple particle problem, right? So then it turns out that the wave function defines the probability density through absolute square, right? So this is the box. We will look at the one-dimensional case because it's the simplest, and generalization to more dimensions is relatively easy. It's a complex wave function. That's why it's already based on that. You could sort of sense that the wave function itself is just an auxiliary construction. It cannot be anything real because the function itself can be complex, right? So how do you interpret complex wave function? Only by forming some real quantities out of it. And one of the most straightforward way to form the real quantities is to take the psi times psi star. Here note that generally function is of space and time coordinate. I skip the time coordinate, assuming it's there, but we just don't write it for simplicity, because this is essentially function at a particular time, and that's how we go. Like at later time, maybe it could be different function according to Schrödinger equation, but at a fixed time, this is just a function of x. All right, and then at a fixed time, the probability density of where my particle is given by the absolute square. What probability density is? It's this quantity that defines the probability. So because we're working with the situation where our kind of random variable where the particle can be is a continuous, so that's a different story than the situation where you're throwing a dice and then there are only 6 possible kind of outcomes from 1 to 6. Here the idea is that you have a space, right, and it's potentially infinite, from minus infinity to plus infinity. So your particle, in principle, somewhere in the finite subspace of this space, right? You could ask questions like, if it's from A to B, what's the probability of finding my particle from A to B? And if you're, and it's given by this integral, because simply the probability of finding the particle between minus infinity to plus infinity will be 1. So the particle exists somewhere, right? So in the full, if you integrate over the full space, the probability is 1. But if you just look at the part of the space, that will deter like a absolute square of the function. If let's say we have a psi of x absolute square shown like this, so then the area under the curve between A and B, that's the probability of finding the particle there. Okay, and that's why we're looking for a solution of Schrödinger equation to determine where can I find my particle. And in the simulation I showed earlier, you saw the red and blue wiggles. So those were real and imaginary part, but the magenta thing was absolute square, right? So the magenta was showing how the probability density was changing in time, because you could see now the snapshots. If we start with probability density being here, let's say, and at later time it moves here, right? So then at the early time, there is a 100% chance of finding my particle here, and at later time, it's 100% already here. Okay. Of course, this is a very simple case, which is which I drawn here, that like classical situation, but in reality, things could be more complicated and more delocalized, where particle with some probability could be either here or there. So that those situations were closer to the second simulation I showed you, where we looked at a double well problem. There, particles started initially like this, but then at later time, it was delocalized over two well. And if you start looking for your particle, then there could be time where it's a 50% chance of finding it in this well and 50% chance of finding it in that well, right? So this is this could be a situation, and that's why we're solving time-dependent Schrödinger equation. And then from the wave function, we could get the probability distribution. Please do not confuse probability distribution with probability, because those are two different quantities. Probability density or probability distribution is the function of space. Our probability is usually a number between 0 and 1, telling you what is the probability of finding, in this case, probability of finding particle between A and B. Okay, yeah. In the NMR spectroscopy, you have spin, right? And there, the space of the spin variable is either spin up or spin down, or it's a superposition of up and down in the perpendicular plane. So there you could ask the question, is my spin up or is my spin down, or is my spin in perpendicular direction, right? So we will talk about spin later, but it's very like the algebra is somewhat different, because for the spin you have only two states. Here you have infinite states, a number of states, but because the wave function can be in well, it's kind of pretty much anywhere, right? While spin has only two states and the superposition of those, right? So spin has a fewer states to consider, but still, because of that superposition, you can have spin probably is like a version. Very frequently, people like to illustrate quantum effects using spin, because it's like a coin. Spin up or spin down is coin flip, like heads or tail, right? But because of the superposition, it may be in the state of neither up or down, but in the superposition of two states, right? So here, for the wave function, the spin situation is close to this double well, because you could associate function being in one well with spin up and function being in another well spin down, and it can also be somewhere in between. Okay. All right, but our time is up, so we will stop here. I'll be happy to answer any further questions, but this is all.